Hello everyone! In this numerical computing tutorial, we explain the basics of the fixed point iteration for solving nonlinear equations. We also explain how to implement the fixed point iteration in Python in order to solve nonlinear equations. The motivation for studying the fixed point iteration comes from the fact that this algorithm is the basis of a number of numerical algorithms used in control engineering, linear algebra, and machine learning. Okay, let's immediately start. The fixed point iteration is a simple method for solving nonlinear equations. Consequently, it's very easy to implement this method in Python or in some other programming language. It has a scalar and a matrix form. In this tutorial, we explain the scalar form of the fixed point iteration. The goal is to solve a nonlinear equation having this form: f of x is equal to 0. Here f can be linear or nonlinear function. For example, our nonlinear equation can look like this: f of x is equal to sine x and equal to 0. Or we can consider a quadratic equation: f of x is equal to x squared plus 3x plus 2 is equal to 0. Or we can consider, for example, this equation: sine x minus x is equal to 0. Or you can imagine any form of a nonlinear equation. Instead of solving f of x is equal to 0, we solve an equivalent problem that looks like this: x is equal to g of x, where this function g is a linear or a nonlinear function of x. We can always transform the original problem in the equivalent form. Let's show this by using these examples. The first example is sine x is equal to 0. Now, if we add x to both sides, we will get sine x plus x is equal to x. And over here we see that g of x is sine x plus x, and we obtain the equivalent form: g of x is equal to x. How about the second example? Let's transform this example. We have x squared plus 3x plus 2 is equal to 0. Now, on the left-hand side, we need to have x. Consequently, we transform this equation like this: 3x is equal to minus x squared minus 2. Consequently, we have that x is equal to 1 over 3 multiplying minus x squared minus 2, or we can write this equation like this: minus x squared minus 2 divided by 3. From here, we see that g of x is minus x squared minus 2 and everything divided by 3. However, the form of g of x is not unique. And let's explain this by using this example. Instead of transforming this equation like this, we can do something else. Let's express x squared from this equation. And let me now just draw these two lines such that you don't get confused. From this equation, we have that x squared is equal to minus 3x minus 2. Consequently, from this equation, we have that x is plus minus square root of minus 3x minus 2. Over here, we can say take either a positive or a negative branch. I will take a negative branch. Consequently, I can say something like this. X is equal to minus square root of minus 3x minus 2. And in this case, we see that g of x is actually minus square root of minus 3x minus 2. And we see that the form of g of x is not unique, although the original problem looks like this. And this is very important to keep in mind. You have several choices, or an infinite number of choices, to be more precise, to choose g of x. Every choice of gx might produce different convergence of the method that we will explain in the sequel. And the proper choice comes with experience. That is, a user that is more experienced will figure out what should be the proper choice of g of x. And in addition, there is a theorem stating the conditions under which the fixed point iteration will converge, and while selecting g of x, you should always keep in mind that theorem. And the third equation is straightforward, namely, from the original form, we can simply express x as sine x. And that's it. Simple as that. Next, we need to define the fixed point denoted by x star, and we need to define the fixed point iteration. Let's start with the fixed point x star. A point denoted by x star that satisfies this equation, x star is equal to g of x star, is called the fixed point of the function g of x. The fixed point iteration is a method for iteratively computing the fixed point x star that satisfies this equation. And the fixed point iteration method, or the algorithm, is defined like this. X k plus 1 is equal to g of xk, where k is the iteration index, and we obtain xk plus 1 for fixed value of xk by propagating the function gxk. That is, this function over here, or better to say, this recursive relationship is propagated for k is equal to 0, 1, 2, 3, and until convergence, or until an error defining a tolerance of convergence is smaller than some prescribed value. That is, for large values of k, xk will approximate x star. On the other hand, since x star is the fixed point, it's at the same time the solution of our original nonlinear system given over here. That is, we can write over here that f of x star is equal to 0. And consequently, we solve this equation over here by using this iteration. We simply pick an initial value of x0 and we propagate this equation to obtain x1, then again we propagate to obtain x2, x3, etc. Let us summarize what we learned so far. We want to solve this nonlinear equation. The first step is to transform this equation into this form, x is equal to g of x. And we learned by considering several examples that we can do it quite easily. Then the third step is to define the fixed point iteration on the basis of this equation. That is, we define this iteration, xk plus 1 is g xk, where the fixed point iteration is propagated for k is equal to 0, 1, 2, 3, etc. That is, a user selects x0 and we simply propagate our iteration to obtain x1 as g of x0, then x2 as g of x1, then x3 is equal to g of x2, x4 is equal to g of x3, etc. At certain point we will stop the propagation, and usually in practice we stop the propagation when xk plus 1 minus xk, that is, two subsequent or neighboring values of x are smaller than some tolerance value epsilon that's prescribed by the user. For example, epsilon can be 10 to the minus 4 or 10 to the minus 6, depending on how accurately you want to approximate the solution. Here's a little bit of theory on the convergence of the fixed point iteration. Namely, the convergence of the fixed point iteration is not guaranteed and it should not be taken for granted. That is, the convergence of the fixed point iteration mainly depends on the form of the function g of x and how we generate an initial guess. So let's state this theorem, giving us conditions under which the fixed point iteration will converge. Let us assume that the function g of x is continuously differentiable on some interval from a to b. The function g of x is such that g of x takes the values in this set for all x inside of this set. And then let us assume that there exists a constant c smaller than 1 and greater than 0 such that the first derivative of g of x is smaller than or equal to this constant for all x inside of this interval. That is, the constant c is a constant that bounds the first derivative of g of x. Then the series of points generated by the fixed point iteration will converge to the fixed point for any initial guess inside of that interval. Furthermore, we know that the fixed point iteration will be inside of that interval. Okay, let's start with the Python implementation of the fixed point iteration. As a test case, we will consider a function f from the beginning of this video. That is, we'll consider this function. F of x is equal to x squared plus 3x plus 2. We have seen that there are two forms of the function g for this function. In the first form, the g function looks like this. It is 1 over 3 multiplying minus x squared minus 2, and the second form of the function g is g of x is minus square root of minus 3x minus 2. Of course, you can consider some other forms. However, in the interest of the brevity of this tutorial, we will consider only these two forms. The first step is to define functions f and g. So here's our f function. We accept x, and for the given value of x, we return f of x that I simply denote here by y. And here's the first version of the g function. Again, we accept x and we return the first form of the g function. That is, we return this value over here. Then, over here in this function, we accept x and we return the value of g defined over here. And you can see how we implement g1 and g2 in Python. That is how we implement these two functions. That is, we will compare fixed point iteration and its convergence for these two forms. Next, we need to define a function implementing the fixed point iteration. To remind you, the fixed point iteration looks like this. xk plus 1 is g of xk. Here's the function that implements the fixed point iteration. First of all, we need to pass the function defining g, and we do it over here. And previously we defined two forms of the function g function and g function 2 that you can see over here. And when we actually call this function, we will pass g function 2 as this parameter gf. Then we need to pass the initial guess, that is, we need to pass x0. Then we need to define the tolerance error for stopping the fixed point iteration. Namely, the error is computed like this: absolute value of xk plus 1 minus xk. And when this error falls below the tolerance error, the iteration will stop. And the tolerance error is actually the parameter defined by user. Over here, I assume the default value of 10 to the minus 6. Then we need to specify the max number of iterations. Namely, it might happen that this tolerance error condition will never be satisfied and we will have an infinite loop. Consequently, it's always a good idea to define the max iteration. Let's go inside of the function. K is the iteration index. We start from 0. Then we initialize xk. Xk will store the current value of xk written over here. And we set it to be equal to initial guess. Then we initialize the error. Initially we assume that the error is huge because we want this iteration to be executed. And we print iteration number k and the current value of xk. Good. Here's the while loop that implements the fixed point iteration. Here we propagate the fixed point iteration, that is xk plus 1 is gxk. Then over here we define the error. Here's how it's defined. And then we update the variables for the next iteration. Xk becomes xk plus 1, k becomes k plus 1, and we simply print. Then once this while loop completes, we return xk. This while loop will be executed and it will run when k is smaller than max iteration and error is larger than tolerance error. Whenever any of these two conditions becomes not true, that is, it's not satisfied, the while loop will break and we will return the current value of xk. And that's it. Simple as that. Before we explain how to use these functions, let's go back to our original problem. Our original problem is to compute the zeros of this function. F of x is equal to x squared plus 3x plus 2. And since this is a quadratic equation, we can easily compute zeros. The zeros are x1 is minus 2 and x2 is minus 1. I deliberately selected this problem since I can analytically compute the zeros and consequently I can verify the accuracy of my fixed point iteration. The first step is to set the initial guess. Here I'm guessing x0 is minus 1.5. Then I need to define the max number of iteration. Then I define the tolerance error. And over here I'm using the first form of g function. That is, the g function in my case looks like this. It's a simple form that we previously derived. However, let's write it again. 1 over 3, and then we have minus 2 minus x squared. And that's precisely the form defined over here. 1 over 3 minus x squared minus 2. Good. Let's continue. Then what do? I'm simply computing the solution by calling the fixed point iteration function. I specify my g function, x0, tolerance, and max number of iteration. And finally, once this is computed, I check the value of fx for the computed solution in order to verify how close is the solution to the actual solution, that is, to make sure that f of x should be equal to 0 or close to 0. Okay, so let's run this and let's see what is the output. I will select everything from here to here and let's run it. Okay, relatively quick. First iteration, second, third, fourth, fifth, 10 until 28. And we can see the final value of x. Let's see. Here it is. Very good. We converge to one of the roots. And let's check the accuracy of the solution by evaluating the function. And we can see this value produces f that's very close to 0. Okay, let's see now what happens if I change the initial guess. Currently, I'm computing the first 0 located at minus 1. How about if I specify x0 to be minus 3? And let's see what happens. Bang! Divergence. And this is very important. Now, if you go back to the theorem, we can see that the conditions of the theorem are not satisfied in the range in which this x0 is. And this causes divergence. Consequently, the drawback of the fixed point iteration is that you might diverge. However, with the smart choice of the function g, you might ensure convergence. Let's return this initial value to minus 1.5 and let's use the second version of g. Again, I will quickly write my function and I will write the g f of x is x squared plus 3x plus 2, and this is equal to 0. Now I have that x in the second form is minus square root of minus 3x minus 2. And that's precisely what is defined in this g function 2. And let's test this g function 2. Again, I will just change the initial condition and I will call fixed point iteration by passing g function 2. And let's see the output. Bang, here we are. And we can see that we are actually converging to the second root, which is super interesting. Now, why I chosen the negative part over here? I chosen the negative branch in order to make sure that this x over here is always negative and that I'm actually not going into the complex plane. Namely, if the argument of the square root becomes negative, the number becomes complex and we cannot use this iteration anymore. This is very important. Now, let's change the value, for example, to minus 2.5 and let's see what happens. Will we converge or not? Again, we converge to 2. What happens if we put like 0.8? Will we converge to 1 or will we converge to minus 2? And we can see an issue happens. Again, you see that we are diverging, and this is again one of the drawbacks, and you can see that the conditions of the theorem might not be satisfied. Anyway, the purpose of this lecture is to illustrate how to implement the fixed point iteration. There is a method to always choose a convergent fixed point iteration. However, this is for more advanced students. That's all for today, and thanks for watching.